Okay, looks like you were able to do those problems. Let's take a look at that. E equals 3 minus 7x squared. Okay, let's scroll down so we can look at the check. 1/14. Okay, looks good for the first problem. Excellent.
Okay, cool.
2. 3x squared minus 2. Okay, good. Let's look at the check. Okay, that looks good too. Let's keep going. So this one was a little tricky because I think might be one of the first examples that used t instead of x. But it looks like you were careful to shift to using t instead of x. So that looks good. Let's look at the check. Okay, that looks good to me too. Great. Okay, so this problem could be tricky because you have to separate out the 1/8 times 1 over x times natural log x to the 5th, but you use the algebra techniques that we talked about to do that. Okay, so let's look at your check for that. Okay, let's go to my screen for a moment.
Okay.
So in your solution, you rewrote the integral like this, and then you substituted in x du for dx.
Right.
And now the x's cancel. and all you have is u's. So that is correct. That will work. I think it's a better process, though, to first, as you've done on the other problems, rewrite the integral so the x's are close to each other.
Okay.
And then you can rewrite this so it looks like that. And we can just replace the 1 over x dx in one fell swoop, like so. Now, both of these methods are correct. There's nothing wrong with the way you did it. In fact, sometimes the textbook does it this way. But this approach is a better way to think about it because it helps you to come up with the right substitution. This reminds you that you're trying to come up with a substitution whose derivative is also in the integral, so you can substitute it out in one fell swoop. So even though the way you did it is correct, I think that it will help you to think about these problems if instead of substituting in for dx, you try to substitute in for all the x's, if you see what I'm saying. Mm-hmm. Rewrite the integral, so all the x's are close to each other, and then try to solve over here on the side for an expression that matches what's in the integral. Like I'm saying, there's nothing wrong with what you did. You wouldn't lose credit for it, but I think in the long term, it'll improve your substitution techniques if you think about the problems this way instead. On the other hand, if there's a problem where this is tough for you, then this method is also okay. So this method's an okay method if this approach doesn't seem to be working for a particular problem.
Okay.
But when possible, I think it's better to rewrite the integral first so all the x's are close to each other. And then you can do it this way. It'll build up better substitution techniques there. But in any case, you did get that problem correct. You would get full credit for that. Let's go back to your screen. Okay, so that problem was correct, so we can move on to the next. Let's see. Okay, so in this problem, it seems like you used that method I was just suggesting. You wrote the thetas next to each other in the integral, 1 over theta times theta. Or did you?
Let's see. I moved this over, and then I subbed in.
Okay, so you maybe didn't quite do it the way I was suggesting. Notice what you could have done is, so go over to the right-hand side. The most useful term was the second line, du equals 1 over theta d theta. Well, you have a 1 over theta d theta in the integral, so you can substitute that out in one fell swoop. What you actually did is you substituted in a theta du and then you cancel. Like I said, there's nothing wrong with that. Sometimes the textbook does it that way, but I think it builds better thinking skills for these problems if you're seeing how you're getting rid of all the thetas in one fell swoop. So again, it would be a good idea first to move the 1 over theta close to the d theta, and then off to the side, see how you can substitute that out. I don't want to make too big a deal about that. You did do this correctly, but I think that it'll improve your abilities for these problems if you do it the way we were doing it in the tutoring. In any case, you got the right answer. So let's move down. Okay, that looks like a good check. Good. Okay, good. So this was a trick question. This was a trick question because you don't need substitution for this question. I just wanted to test to make sure that you were noticing that you don't always need substitution. Sometimes you can just do the integrals directly. That's important because on the final, obviously, you'll see a whole mix of problems. So you can't assume that every problem on the final is going to require the substitution technique. So it looks like you didn't fall for the trick. You saw here that you didn't need substitution, so that's good. This is a little bit of a tricky integral, but you remembered how to do that. You remembered the algebra simplifications you needed to do that integral. So that's good that you're remembering that problem. That's good, and you checked it correctly. All right, good. Okay, and this was some review of some stuff we talked about last time, how we could rewrite tangent and cotangent. So we have to have that memorized. It looks like you did both of those correctly. Okay, so those were the problems?
Yep.
Okay, so it looks like I actually gave you quite a few problems there. It's good that you had the time to go back and redo all of them. I think that should definitely help us to get through this section easier, more quickly. So that's good. That was a lot of problems, but I don't think there were any mistakes in there.
Cool.
So that's good improvement. Like I said, your technique might benefit from doing the problems slightly differently, but like I say, it's not a huge issue. You definitely used a correct approach on those. Okay, so that's good. You had the time to do those carefully and avoid mistakes. That's some good progress. Let's go back to my screen. Let's see. Okay, well that definitely is a big help. So that means we don't need to review that material from yesterday. You got those right, so we can move on to some harder problems from this section. Let's see.
Okay.
Okay. Well, this is a little different from the problems we did yesterday, but it's not that different. We can still use similar techniques, so try this problem on your screen.
Okay. So the antiderivative of 1 over square root of 1 minus x squared. That's sine inverse sine x. This is I'm not sure what the antiderivative of inverse sine is. I think we've gone over that.
Okay, so yeah, so do you think, remember that we have to know which antiderivatives we know and which we don't. So do you think, is the antiderivative of inverse sine something we know?
I think we've gone over it, but I'm not sure.
Yeah, that's a little tricky. Actually, do you have that table of antidifferentiation formulas?
Mm-hmm.
We kind of have to have that memorized, but right now let's take a look at that. So look to see if inverse sine is in there?
Oh, the antidifferential. No, I guess I don't have that.
Oh, you're saying you don't have the table of the anti-differentiation formulas?
I don't think.
So here's that table I was talking about. So that would be a
Okay.
good thing to find again. Now, you really kind of have to have this memorized. You have to have this memorized. But in the meantime, let's look at the table here. So what are we looking for here?
We're looking for the antiderivative of inverse sine of
That's
x.
right. Now, where are we looking for it? In the function
don't know
column
that.
or the antiderivative column?
In the function column.
Yeah, it has to be in the function column. So does it look like we know that antiderivative?
No.
No. Okay, so that's important. You have to know when you need substitution and when you don't. And the only way to know that is to know what antiderivatives you know simple rules for. So this is an important table to have memorized. I think we kind of put this in the tutoring notes in the past, but also here's the copy your instructor gave you. So notice there's not that many entries here. There's not that many entries. There's not that many antiderivatives that you know, really. So you kind of have to have this memorized. Do we know the antiderivative of this function?
Yep.
And
Inverse sine of x.
do we know the derivative of this function?
We do.
But do we know the antiderivative of this function?
No.
No, because if we did, it would have to be in the function column. Okay, so that's something that's worth memorizing for the final coming up. You have to know which antiderivatives we know and which ones we don't know.
Okay.
So this would be a good table to dig out again. Let's stay on my screen for a moment. Now, if I understand correctly, what you were trying to do on that problem was this. You were trying to split this integral up into these two separate integrals?
Right.
Okay, is this step legal?
Yeah. I was just following what I've been doing previously, I think. I'm splitting up the fraction.
So is this legal? Yes, that's definitely legal. But you were doing more than that. You were first splitting up the fraction, and then you were doing this. Do you see how these are two separate steps? It's definitely legal to say that the fraction can be split up into these two separate terms. But then you were going beyond that, and you were saying, now the way to find the integral here is to find the two integrals separately and multiply them together. That's a totally different step. This is, again, where it's so important to try to take smaller steps. What happened here is you kind of went straight from here to here, although you didn't quite write it out. It's better to write down each tiny little step we're making to check whether it's legal. So going back to here, is this something legal that we can do with integrals? Is the integral of a sum the sum of the integrals?
No.
This is legal. This is something we do all the time. We've been doing this all the time. Whenever we're finding integrals, with sums, we generally split them up. For example, how would you do? How would you evaluate this integral?
The natural log of x plus cosine of x plus c.
Where did you get the natural log of x from?
Because it's the antiderivative of 1 over x.
Great, good. And what else did you have here?
Cosine of x.
Where did you get the cosine of x from?
Because we take the antiderivative of just one term and then plus c.
Why take the antiderivative of only one term? Okay, looks like
Correct.
there's some confusion here, so this would be a good thing for us to review. So actually what you would do here is you would do this. You have to take the antiderivative of both terms.
Okay.
What's the antiderivative of cosine x?
Sine of x.
Okay, I think we were getting a little confused here because we've been doing this on lots and lots of problems. Whenever we have sums, we've been taking the antiderivative of both of the terms and then just adding them together. The antiderivative of a sum is the sum of the antiderivatives. The antiderivative of a sum is the sum of the antiderivatives. How about this? Is this legal? And the answer is yes, this is also legal. This is what's called the constant multiple rule, right?
Mm-hmm.
I think this is what you were thinking of a moment ago when you said you didn't need to take the antiderivative of the cosine. You were probably thinking of this. We've seen that when you have a constant multiplied times a function, you don't have to take the antiderivative of the constant, you just pull the constant out of the integral. You must have gotten that confused with this case here. So when you have a constant multiplied by another function, you don't have to take the antiderivative of the constant, you just pull it out of the integral. But that doesn't apply in this case. Here we did not have a constant multiplied by a function, we just had the sum of two functions. Well, when you have the sum of two functions, you really do have to take each of their antiderivatives separately. When you have the sum of two functions, you really do have to take their antiderivatives separately. So here we were using the sum rule, and here we have the constant multiple rule. The problem here is that we've been doing these antiderivatives a little bit. I've been teaching it a little bit sloppily because we've been doing it. We've been skipping steps. We haven't been writing out each of these steps. So now is a good time to write out these steps so we can see exactly what we're doing. So how do you find the antiderivative of the sum? Well, you just take the antiderivative of each term and add them together. How do you find the antiderivative when you have a constant multiplied by a function? You just find the antiderivative of the function and multiply it by the constant. And all the stuff we're talking about here, this doesn't really have anything particularly to do with the substitution method. Right here, none of this is particularly related to the substitution method. These are just general rules for finding antiderivatives. Okay, so here we have, let me write this correctly. So here we have the antiderivative of a product. So it seems natural that we could just take the antiderivative of the first function and take the antiderivative separately of the second function and just multiply those things together.
Mm-hmm.
But that doesn't work. This is not correct. This is wrong. There's a big not equal sign here. You can't do this for products. There is no product rule for antiderivatives the way there's a sum rule for antiderivatives. There's a nice simple sum rule for antiderivatives. The sum rule is to find the antiderivative of a sum, just find the antiderivative of each term separately and add them up. The antiderivative of a sum is equal to the sum of the antiderivatives. But the antiderivative of a product is not equal to the product of the antiderivatives. We never really quite talked about this before, but now's a good time to talk about this. Do you see what I mean when I say here that this says that the antiderivative of the sum is the sum of the antiderivatives? Do you see how that applies here?
Yep.
But is the antiderivative of a product equal to the product of the antiderivatives?
No.
No. Okay, that shouldn't surprise you because if you remember, it kind of works similarly for derivatives. If you remember with derivatives, we saw that the derivative of a sum was just the sum of the derivatives. But is the derivative of a product equal to the product of the derivatives?
No.
No, it was much more complicated than that. Remember that, so this doesn't work. Instead, you had a much more complicated rule, the product rule. The derivative of a product is not the product of the derivatives. You have to use a more complicated rule. So similarly, antiderivatives work nicely and smoothly for addition and for subtraction. The sum of an antiderivative is just the antiderivative of a sum is just the sum of the antiderivatives. But antiderivatives do not work nicely. They do not work smoothly for products. In fact, there's no product rule at all. At least for derivatives, there was some product rule, even though it was kind of complicated. But for antiderivatives, there's no product rule. Maybe I should write that down. There is no product rule. For antiderivatives. That means there's no simple way to take the antiderivative of a product. There's no way to split it up into two smaller antiderivatives. That doesn't mean that it's impossible to take antiderivatives of products, but you can't do it just by splitting it up into the product of two antiderivatives. Okay, and that's I think what you were trying to do on this earlier problem. So let me write this correctly here. So this step was correct. This step here was correct because this was just algebra. You were just rewriting the fraction as two separate terms. That was correct. But then you tried to go on and take the antiderivative of each of these separately. Now, you didn't quite write it out. You didn't write it out with separate integral signs, but this is what you were doing. You were trying to take the antiderivative of this inverse sign, and you were trying to take the antiderivative of 1 over root 1 minus x squared, and presumably you were going to multiply those two answers together. So even though you didn't write it out, this must have been kind of what you were doing in your head. But this turns out not to be legal. So this line is legal, but this line is illegal. We can write it like this, but we can't take these antiderivatives separately. So that's a technique that's not going to work for us on that problem. Let's go back to that table that your instructor gave you. So notice here your instructor is reminding you this is the constant multiple rule. Do you remember what does capital F stand for?
The antiderivative
of lowercase f.
Right.
So they're saying here if you have a constant times a function, just take the antiderivative of the function and multiply it by the constant. That's the constant multiple rule. And here they're doing the sum rule. So what does capital F stand for?
The antiderivative of lowercase f.
And what does capital G stand for?
The antiderivative of lowercase g.
So they're saying here's the sum rule. If you're trying to take the antiderivative of a sum, just take the antiderivative of one function and take the antiderivative of the other function and just add them up. But notice there's no line here for f of x times g of x, right? Notice how your instructor did not include a line for f of x times g of x because there is no product rule for antiderivatives. There is no special way to simplify a product. There's a way to simplify a constant times a function. And there's a way to simplify the sum of two functions, but there's no way to simplify the product of functions. That's another way of saying what we just talked about. So when we did this before, I was a little bit sloppy, and I never really talked about these two lines. I just focused on all the rest of the table. But we should have also been talking about these lines here and talking about the constant multiple rule for antiderivatives and the sum rule for antiderivatives. And also what I should have done is I should have emphasized there's no product rule for antiderivatives.
Okay.
There's no. So is there a sum rule for antiderivatives?
Yep.
Is there a product rule for antiderivatives?
No.
Although it's a little bit complicated, there is a product rule when one of the things is a constant.
Right.
There is a product rule for a constant times a function, but there's no product rule for a function times a function. There's a product rule for a constant times a function, but there's no product rule for a function times a function. Okay, so let's think about this problem again. So the problem was this. And it turns out that there doesn't seem to be any simple way to solve this using our earlier techniques. It doesn't do us any good to separate this into two fractions because we don't know what the antiderivative of inverse sine is. And even if we did, there isn't any product rule for antiderivatives. So instead, we have to use the substitution technique. Instead, we're going to have to use the substitution technique. What substitution should we make? U equals what?
Let's see. Well, the problem is the inverse sine of x, so we need the u equals u equals x to the negative 1.
Like this?
Yep.
Okay. Now, we'll have to work on that a little bit more, too. One thing is, you were saying the problem is the inverse sine. But after all, actually, they're both problems. We don't know how to take the antiderivative of... Well, I guess that's not true. The other one, we do kind of know how to take the antiderivative. So I can see why you would say that's the product. So that's a reasonable thing to say. Now, remember, so is this an exponent?
Yep.
Is this an exponent?
Yep.
So is this negative 1 an exponent?
No, it means inverse.
Yeah, remember we've talked about that a bit in the past. Remember we called that an abusive notation.
Right.
This looks like it's an exponent, but it's not an exponent. It stands for inverse sine. So there really isn't any reason to use a negative 1 exponent here because there's no negative 1 exponents in the original problem. Well, remember we want to make a substitution for something in this problem whose derivative is also in the integral. Remember we want to make a substitution whose derivative is also in the integral.
Okay.
I'll just tell you what the answer is. This is the correct, or here's a possibility. We should consider this. Now, will this help? Well, what's the derivative of inverse sine of x?
1 over the square root of 1 minus x squared.
And does that appear in the integral?
Yep.
That's why this is the correct substitution. This is the correct substitution because its derivative is also in the integral. So that's tricky. But this is actually, once we look at it in the right light, this will be very similar to the problems we did yesterday. This looks quite different, but once we look at this in the right light, this turns out to be very similar to the problems we did yesterday. This is the correct substitution because we want to make a substitution whose derivative is also in the integral. Okay, so here's the substitution that we're going to make. What should be my next step?
Okay, so now we can rewrite the integral as the integral of sine of u. Sorry. Yeah, it was the integral of u over square root of 1 minus x squared dx.
That's right. So we just made the substitution. Now we make the substitution. Good. Then what?
So let's see. Okay, so now we can rewrite the integral as the integral of u times 1 over square root of 1 minus x squared dx.
Excellent. This is legal. It's legal to write this as two separate fractions. That's just algebra. It would now be illegal to split this into two separate integrals. We're not allowed to split it into two separate integrals because there's no product rule for antiderivatives. But it's perfectly legal to write what's inside the integral as two separate fractions. That's a technique we were working on yesterday. Well, that was a good idea because we wanted to rewrite this so all the x's are together. We wanted to rewrite all the x's together. Now what?
Okay, so now we need to solve for dx. So we need to re-express du over dx equals the derivative of inverse sine, and that is 1 over the square root of 1 minus x squared.
That's the whole reason why this was a good substitution.
Right. Now
That's good.
Now we can rewrite that as du equals 1 over square root of 1 minus x squared times dx. And now we can multiply by, well, yeah, we can multiply the left-hand side by 1. Actually, hold on 1 second. We divide it. Okay. So we can divide, like I would just divide here, confuse myself. So I would rewrite this as du over 1 divided by square root of 1 minus x squared. And then I guess we can, yeah, I guess we can just multiply by the reciprocal. So it would be square root of 1 minus x squared du equals dx.
Okay, that is a legal step. That's a legal step. I think there's a better way to think about it, though. Remember that our goal here is to get rid of all the x's. Our goal is to get rid of all the x's here. But notice, so what we really want to do is we want to solve this equation so it looks like this. We want to solve for 1 over root of 1 minus x squared dx. Maybe that feels weird because we usually solve for one variable, not for an expression. But here we're solving for this expression. We're going to solve for 1 over root 1 minus x squared dx.
Okay.
Well, notice we already did that. It's already solved for 1 over root minus 1 minus x squared dx. So we can simply make a substitution. What can we substitute in for this term? Notice how simple that is once we see it. Okay, now the method you were using could get to the right answer. The method you're using could get to the right answer, but this is what we were talking about for the homework problems. Even though it can work, it's really not the best way to think about these problems. It's better, instead of thinking, so what you're trying to do here is you're trying to solve for dx and substitute in for dx. That can work, but instead, try to solve for all the terms that involve x. Try to get all the x's by themselves, and solve for the whole expression involving x. And then that makes the substitution simpler, and it also gives us a better way to think about these problems. It'll improve our thinking skills for these types of problems. Okay, so remember, try to avoid the temptation of solving for dx. Instead, try to get all the x's together in the integral and solve for the expression involving the x's. Okay, so now what?
So now we can take the antiderivative, and it will be, let's see, you put 1 plus 1, 2. So 1/2 u squared plus c.
Plus c. Good, excellent. And then what?
And now we can just plug in u, and u was inverse sine of x. So 1/2 times inverse sine of x squared.
So we'll need some parentheses to show that.
Yep. Plus c. And we're good.
Okay, so here's our answer. All right, so this problem might have seemed harder than the earlier ones, but once we've seen how to do it, we should see it's really the same exact process as yesterday. It's really the same exact process as yesterday, just a little bit trickier to see. How did we know what substitution to make here? Well, it's not always obvious what substitution to make. You might have to use trial and error. But why is this a good substitution? Because its derivative is also in the integral. By the way, notice, do we know the antiderivative of inverse sine?
We don't.
But do we know the derivative of inverse sine?
Yeah.
Notice how we were able to use that to our advantage here. Even though this is about the antiderivative of inverse sine, by using this substitution technique, we actually were able to take advantage of the fact that we know the derivative of inverse sine. And then, because its derivative also appeared in the function, that whole 1 over 1 minus x squared, that whole root disappeared when we did this substitution. Okay, so this was a tricky problem, but I think there's a good chance this will be on the test. So now we saw how to do this. And we also reviewed how there's no product rule for antiderivatives. So instead we needed a substitution approach here. Okay. You have that in your notes? Is that making any sense?
Yeah,
okay.
It does.
Let's try this problem on your screen.
Okay. plus 2. Okay. 3u. Okay.
Okay, so let's replace the dittos in that last line with what we're solving for. That's always a good step, so we know what we've solved for. Okay. There was a mistake in that last line. So taking a look at that last line and see what the mistake is. Yeah, okay, so it'd be a shame to lose credit for that last step because I think you were thinking about that correctly. All right, how could you check that answer?
We could take the derivative of this, and we should get this.
Okay, I think that would still be good practice, but to save time, why don't we make those homework now? So I think that, so for today, to save time, I don't think we're going to keep checking the answers, but I think that would be excellent practice for you. First of all, it would be helpful to be able to check your answers on the test if you have time, but also just more important, the final's coming up soon, and it's been a while since we did derivatives, and these are, you're going to be testing on derivatives anyway on the exam. So it would be good practice to improve our derivative skills that we haven't worked on for a while to keep taking those derivatives. So that would be it would be good if you could find the time to do the homework to redo those, but we'll save time by not doing that together. Okay, so this was pretty similar to the previous question, but it looks like you worked out the correct way to solve that. So is there a sum rule for antiderivatives?
Yep.
Yeah. Is there a product rule for antiderivatives? No. Is there a constant multiple rule for antiderivatives?
Yep.
In fact, you used the constant multiple rule, right? When you took the 3 out of the integral. When you took the 3 out of the integral, you were using the constant multiple rule. But we could not split this up into the product of two integrals. We couldn't split this up. We could make it a product, but then we couldn't make it the product of two integrals because there's no product rule for antiderivatives. Okay, so that's some improvement on that. Let's go back to my screen. Let's try this problem.
Okay. We don't know the antiderivative of inverse tangent of x.
And even if we did, it wouldn't help us because it's all tangled up with the x squared plus 1. Good.
So use substitution, and the derivative of inverse tangent of x is 1 over x squared plus 1. So we separate them, and then we try and substitute for this term. This term. We did that. Take the antiderivative and then plug u back in. Okay, cool. Yeah, that's good, I think.
Okay, good. And we can check that for homework. Let's erase the dittos in the last line with what we're actually solving for. That's just a good habit so that we know what we've solved for, and that will help you to check your answer. So you started with inverse tangent of x over x squared plus 1. And you took its antiderivative, and you got 1/2 inverse tangent of x squared plus c. Now, if you then take the derivative of 1/2 inverse tangent of x squared plus c, what should that give you?
It should give you the inverse tangent of x. Well, actually, I think it'll give you 1 over x squared plus 1.
I'm not sure why you said that.
I'm not, well, sorry, yeah, that's not true. It'll give you the inverse tangent of x over x squared plus 1.
That's the way to check, right? The way to check is to make sure that when you take the derivative of the antiderivative, you should get back to where you started. When you take the derivative of the antiderivative, you should get back to the original function. If we took the derivative of inverse tangent of x, that would be 1 over x squared plus 1. But this was a more complicated function. Okay, well, that's something you can reinforce by checking this in your homework. Okay, so I'll go back to my screen. All right, so that's some practice with how this substitution technique applies to inverse trig functions. Something else I think we're likely to see on the test, how it applies to inverse trig functions. So I'll be on my screen. Let's write down this. Okay, well, this problem is a little different than the ones we did before, but it's also quite similar. We should be able to adapt our techniques to this problem. Well, let's give it a shot. So let's try this problem.
Okay. Derivative of tangent is secant squared. Okay.
Okay, well that was fast, but it looks like it was accurate. That's good. Okay, good. So I think we're building some skills here. So this was not different from the ones we've done before, but you adapted pretty quickly to see what they were going for in this case. Or did us? Did we? Let's see. Uh, uh, okay, yeah. So maybe we were a little too fast. So what was the substitution that you used? U equals what?
Tangent x cubed.
What's the derivative of tangent x cubed?
Oh, okay. 1 over secant squared. Oh, wait. 1 over secant x to the 6.
I'm not quite sure how you got that. But anyway, it would be complicated.
Okay.
You'd actually have to use the chain rule to find that derivative, wouldn't you?
Yeah.
Actually, to find that derivative, the simple rules don't apply there. You'd have to use the chain rule to figure that out. So you can't just say that the derivative of u here is secant x squared. So basically, that substitution turned out to be a poor substitution. That substitution doesn't work because its derivative is too complicated. Remember, we want to use a substitution where it's easy to take the derivative and its derivative is in the expression.
Okay, so the derivative of secant squared x, that is secant x tangent x, I think. Okay. Okay, so
What's the derivative of secant x?
the derivative of secant x is I don't know.
Okay, we're getting a little confused. What happens oftentimes is when people keep moving, these problems require us to keep moving back and forth between derivatives and antiderivatives. And that people tend to start losing their bearings and get confused when they're doing that. They start to get confused between the derivatives and the antiderivatives. Perhaps we should move back to my screen. Okay, so do you know what this is?
Secant x tangent x.
What's this?
Secant x squared.
Say that again, please.
Secant squared x.
Okay, or secant of x in parentheses squared. Okay, good. So how could you rewrite this as an integral?
The integral of secant x tangent x equals secant x.
Plus c. Good. And how could you rewrite this as an integral?
The integral of secant x squared equals tangent x plus c.
Okay. So what about this? How would you go about finding this derivative?
I don't know.
You'd need the chain rule.
Okay.
Do you see what I mean by that? How would you use the chain? Yeah, if you use the chain rule, you could simplify this to work this out. There's no simple rule for this, is my point. There's no simple rule for this derivative. Is there a simple rule for the antiderivative of secant squared x? Is there a simple rule for the antiderivative of secant squared x?
No.
Well, that was this right here.
Okay.
This is the antiderivative of secant squared x. There is a simple rule for it. It's just the tangent, because the derivative of the tangent is secant. But there's no simple rule for the derivative of secant squared x. For that, you'd need the chain rule. Maybe that's something we'll have to review at one point. Okay, so like I say, this is where people start to get confused, even if they kind of thought they had things down before. People tend to start losing their bearings on these problems with substitution because you have to keep going back and forth between antiderivative, derivative, antiderivative, derivative, and people start to get the two things mixed up. They start confusing the derivatives with the antiderivatives. So is there a simple rule for the antiderivative of secant squared x? Is there a simple way to find the antiderivative of secant squared x? It's tangent x. Is there a simple rule for the derivative of secant squared x?
No.
You'd have to use the chain rule for that. Okay. So this might be a good little thing to meditate on a little bit so that we're not getting these ideas confused with each other. So let's see. The problem we were working on was this one. So the substitution you were considering making was this. Well, now, is there any simple rule for taking this derivative?
No.
No. So it's probably not a great substitution. You could take this derivative using the chain rule, but it's not obvious what it's going to be. There's no particular reason to think that this derivative is going to be in the integral. Remember, we need to make a substitution that's in the integral. We need to make a substitution whose derivative is also in the integral. We need to make a substitution whose derivative is also in the integral. And usually it should be kind of obvious to see that. We want to make a substitution where it's easy to take the derivative. We're never going to want to use the chain rule for that. All right, well, it's hard to come up with the right substitution here, so I'll just tell you this is the correct substitution. How can I check that? Well, do we know how to take this derivative? Is there a simple rule for finding this derivative?
Yeah.
Yeah, what is the derivative here? What's the derivative of tangent x?
Secant squared x.
And here that is in the integral. So that's why this is the correct substitution to make, because its derivative is also in the integral. All right, so here's the substitution we're going to make. So what would be our next step?
Wait, I thought that's what I did the first time.
What you did was this. So close, but yet so far. Unfortunately in math, close is not good enough. Unfortunately in math, close is not good enough. You were close. Why is this a good substitution and this a bad substitution? Well, is there a simple way to take this derivative?
Yeah.
Yeah. Is there a simple way to take this derivative?
No.
No, you'd have to use the chain rule again. You'd have to use the chain rule to find this derivative, and that's something you're never going to need to do in the substitution technique. You should never make a substitution that requires you to use the chain rule to find the derivative. You're not going to need that in this class. Okay, so I can see how you could start getting confused here. So notice here, what went wrong here is that your first substitution was kind of on the right track. And when we rejected this, we reversed too far in the other direction and tried to substitute for secant. But we were actually better off with the tangent. It's just that we have to do the tangent and not the tangent cubed. So notice you're not trying to substitute necessarily for a huge chunk. You don't have to substitute for tangent cubed or for secant squared. You can just substitute for anything in the expression whose derivative is also in the expression. You want to substitute for anything in the integral whose derivative is also in the integral. You don't necessarily have to substitute for the biggest possible chunks of the integral. That's tricky. It takes trial and error. All right, so now what?
Okay, so now we can rewrite our integral as the integral of u cubed times secant squared x dx.
Okay, notice it doesn't kill us that we didn't substitute in for tangent cubed. We just get a u cubed. We know how to deal with that. That's fine. Okay, now what?
Okay, so now we need to solve for du. So we can write du over dx in the corner equals, let's see, what is u? The derivative of tangent x is secant squared x. And now we can rewrite that as du equals secant squared x times dx. And now in the integral we can sub in the integral of u cubed times du.
Because we solved for this whole term and we got rid of it. Okay, this is why this was a good substitution. This was a good substitution because its derivative really was in the integral. Okay?
Okay, so now we can take the antiderivative, and that will be 1/4 u to the 4th plus c. And now we can plug back in for u, and our final answer is the integral of tangent cube x times secant squared x dx equals 1/4 1/4 tangent of x raised to the 4th.
So you could either write that like this, or you could write it like this.
Okay.
So either of those is fine. Either of those is fine. This looks more like the starting material, but it's also fine if you put it in parentheses. Either of those is fine. Plus C. Okay. And again, it would be a good homework problem to check this and make sure that we get back what we started with here. Okay. All right, so that one gave us a little bit of trouble. So the hard part when you're using the substitution method is to find the right substitution. So let's review what were the wrong substitutions here. One substitution we tried was this. Why did this turn out to be a poor substitution?
Because we'd have to use chain rule twice.
We'd have to use the chain rule to find its derivative. Yeah,
right.
You'd have to use the chain rule once to find its derivative, but that's more complicated than you'll ever need for this type of problem. And there's no way of knowing whether the derivative of this is really in the integral. I'm pretty sure it isn't. But anyway, or maybe it is. But anyway, that it would make things too complicated for us here. In any case, when you did do this substitution, you didn't use the chain rule for the derivative. You were oversimplifying. So that one doesn't work. And then the next thing we tried was this. Why is this a poor substitution?
Because we don't know the derivative of, sorry, there's no simple rule for taking the derivative of secant squared x.
We need the chain rule again. We need the chain rule again for this. Why did you think this would work? Why did you think this would work? I'll bet you were probably remembering that there is a simple way to take the antiderivative of secant. Mm-hmm. There is a simple rule for the antiderivative of secant, but that's not what we need here. What we need to use that substitution is a simple rule for the derivative of secant, and that doesn't of secant squared x, and that doesn't work. Okay, so this is an important example here to have in your notes. Once I helped you out finding the right substitution, you were able to apply the rest of the method. So we're still using that method correctly here. Okay, you have that down?
Yep.
All right. All right, let's try this problem.
Derivative of tangent gives us secant squared x. 6. Okay.
Okay. Let's rewrite those dittos on the last line. That's a good step there, and I'll check that. Okay, so obviously these are a lot easier once we've seen the pattern. The hard part is shifting from one type of problem to another. So the substitution you made here was u equals tangent theta. Why is that a good substitution?
Because the derivative of tangent theta is secant squared theta.
Which is also in the integral. Good.
Mm-hmm.
Now on the previous problem, you tried a substitution like u equals tangent theta to the fifth. Why would that not work here? Why would u equals tangent theta raised to the fifth power not be a good substitution?
Because there's no simple rule for taking the derivative.
Yeah, it would be too complicated. You need the chain rule for the derivative. That's more complicated than we need on these. It's not obvious whether that derivative would even be in the integral. Okay, all right, well, we made some progress on that now. That was good. I'll go back to my screen. Here's something we talked about at the beginning of our last session. Can you think of any way to rewrite this expression?
Okay, we can rewrite that as x times x to the fourth.
Okay, good. Because if you multiply them, you get back to where you started. Now, obviously, there's a million different ways to rewrite it. You could also rewrite it like this. You could also rewrite it like this. You could rewrite it like this. There's many different ways that you could rewrite it, but the one that's going to be useful to us today is to remember this form of rewriting. Okay.
Okay.
Okay, this problem, we can use the same techniques here as in the earlier problems, but this is a little harder. Although we're going to use the same techniques, this is a little harder than before, but let's give this a shot.
Okay. Derivative of tangent x is secant squared x. Oh. So we can rewrite this as
Okay, that's a good idea. That's a good thought. The problem is, if we use this approach, if you think about it, we're only going to be able to get rid of one of the secant squared x terms. When we take the derivative, one of the secant squared x terms will drop out, but then we'll still have another secant squared x flying around in the integral that we're not going to be able to get rid of. So that was a good idea, but I'll save you some time and say that it turns out that won't work.
okay.
Its derivative is in the integral, but it doesn't account for enough of the integral. So that was a good try, but that substitution turns out not to work.
Okay.
So we'll have to try a different substitution.
So let's see. The derivative of tangent x is secant squared x.
I'll give you a little help with this. This is a little tricky. Let's see. Well, remember we were saying that substitution won't work because it's
Okay.
only going to get rid of one of the secant squared x terms.
Okay. All right. Then I'll try something else.
So now try one more substitution.
Okay. Let's see. Well, if we rewrote this, okay, yeah, I think I know. Maybe not. First, I'm going to rewrite this as secant x times secant cube x. Now we can say that u equals secant. Wait. Let's see. Okay. Derivative of secant.
Okay. Now, why might that be a good idea? Why do you think that u equals secant x might be a good idea here?
Well, at some point, we're going to have 3 secant x squared.
Okay,
And
that's probably not, let's see, that's not the best line to go down thinking. Remember, we want to make a substitution whose derivative is also in the integral. We want to make a substitution whose derivative is also in the integral. What's the derivative of secant x?
Secant x tangent x.
Good, that's right. Is there a secant x tangent x in the integral?
Let's see. Yep.
Yeah, there is now, because you used the clever trick of rewriting secant to the fourth as secant times secant cubed. So there didn't used to be a secant times tangent there, but you've used a clever trick. You rewrote secant to the fourth as secant times secant cubed. Why did you do that? Well, presumably, perhaps you did that so you'd have a secant times tangent there. So that was a good trick. So u equals secant x is a good substitution. U equals secant x is a good substitution because its derivative is now in the integral. However, that was a good move on your part, but then you kind of messed it up a little by substituting in for your first secant x. Even though it's legal to say the first secant x is u, that's going to mess up our solution. We want to leave that as secant x. And we'll see why we're going to leave it that way in a second. Remember, the whole reason this is a good substitution is because the derivative of secant x is in the integral. So we don't want to get rid of that secant x because then the derivative won't be in the integral anymore.
Okay. So the derivative of secant x.
So probably the next thing we should do is, remember our general technique, rewrite the integral so all the x's are together. Because then we know what we need to substitute out. And now we can go back and take the derivative of our substitution. Okay, so do you see now why we didn't want to replace the secant x with a u? It would have been legal to replace the secant x with a u, but then there would be no way to get rid of the tangent x. If we had replaced the secant x with a u, there would be no good way to get rid of the tangent x. Instead, we want to get rid of the secant x and the tangent x and the dx all together in one fell swoop. Also, now you can see why it was a good idea to rewrite secant to the fourth as secant cubed times secant, because we needed that extra secant term to multiply times the tangent x to be replaced. Well, it's kind of hard to put into words, but hopefully that's making sense. Okay, so let's continue.
Okay. Okay, so we had secant to the fourth x times tangent of x. So if we took the derivative of tangent of x, we get secant x, secant squared x. But that's not useful because
So
I'm not quite sure why it's not useful.
You're wondering why not use u equals tangent x?
Right.
So what's the derivative of tangent x?
Secant squared x.
So that would have let us get rid of one of the secant squared x terms, but there would still be another secant x squared term that we wouldn't be able to get rid of with that approach. It didn't account for enough of the rest of the integral. Remember, we need to try to make a substitution that gets rid of all the x's. So if you had used u equals tangent x, you could have gotten rid of one of the secant squared x terms, but that would still leave you with another secant squared x term that you can't get rid of. So that substitution turns out not to be helpful. Whereas notice in this case, with this substitution, you were able to get rid of the entire secant x tangent x term, so there were no x's at all left in the expression. We need to try to make a substitution that will allow us to get rid of all the x's. We need to try to make a substitution that will allow us to get rid of all the x's. Because remember, we can't take the integral until there's only one variable. So if you use the u equals tangent of x, that would only get rid of a secant squared x term. That would still leave another secant squared x term, because secant to the fourth equals secant squared times secant squared. So it's worth a shot, but it turns out not to work. Instead, when you use the u equals secant term, so sometimes you have to do these by trial and error. So you have to remember that your first approach might not work. You have to use trial and error, and if it doesn't work, you have to be open to the possibility that it might not work and then try a different substitution.
Okay, so why is it bad to, I mean, like if I used u as tangent of x, why is it bad to have another secant x still in the integral? Is it because we can't take the antiderivative of that? Is that why?
That's right.
Okay. Okay. Like I'm just trying to make sense, or else I'm just going to try and memorize it, and that's not effective. So, okay.
Okay, so are we done with this problem?
Yeah.
All right, let's rewrite the dittos in the last line so we can see what we were solving for. And again, this would be good to check as homework. Okay, so to review, we said the trick here was to break one of the secants out of the secant to the fourth, because then you had secant x tangent x, which is an antiderivative that you know. But notice then again, you did not want to plug the u in for the secant x. You didn't plug u in for secant x, even though you could have. Instead, you moved the secant x over to the tangent x, and you got rid of that in a different step. Well, this is hard for me to put into words, but hopefully those steps are making sense. Let's go back to my screen. I just want to sketch out why this substitution won't work. Let's sketch out why this substitution will not work. Well, first of all, would you agree that it's legal to go from here to here?
Let's see, yeah.
Because secant squared times secant squared is secant to the fourth. So now I plugged in u for tangent x.
Okay.
So do you see how I went from here to here?
Yep.
Now, the next step is I'll take du dx. So what would du dx be here?
Let's see. Secant squared x. And then du equals secant squared x dx. Okay.
But now we're in trouble because we don't want to get rid of. That would only let us get rid of this.
Mm-hmm.
But we need to get rid of this too. This is why this substitution, so what I'm trying to sketch out is why this substitution doesn't work. This substitution doesn't work because we can't get rid of all the x's. The substitution technique only works if it gives you a way to get rid of all the x's. If you actually do the substitution here now, you'll have this.
So if we did do it this way by accident, you could still use chain rule.
Well, let's take it one step at a time. So what can I plug in now for secant squared x dx?
Du.
All right, but now we're stuck. There's nothing we can do. You said we could use chain rule, but this is an antiderivative, not a derivative. You can use chain rule for derivatives, but we can't use chain rule for antiderivatives. So we can't use chain rule here. There's nothing we can do. We're stuck. There's no further progress we can make on this. You can't take the antiderivative when there's both u's and x's. You can take it when there's only x's, or you can take it when there's only u's, but you can't take an antiderivative that involves two different variables. So this is why this substitution doesn't work. It doesn't work because it doesn't give us a way to get rid of all the x's. It doesn't work because it doesn't give us a way to get rid of all the x's, whereas we saw that the other method did. I don't know, does that make any sense?
Yep.
Okay, so that's, like I say, sometimes you have to do these by trial and error. So you have to keep in mind that you can't just trust that your first answer is correct. Your first answer might be incorrect, so you can't force it to work, is what I'm saying. You can't force a substitution to work if it's not working. If something's not working, you have to recognize it and try something else. These have to be done by trial and error. This substitution seemed reasonable, but it turns out not to work because it doesn't give us a way to get rid of all the x's. Instead, the substitution, so what I'm showing here is why this substitution doesn't work. This is why u equals tangent x does not work. Instead, the substitution that did work was u equals secant x, because that allowed us to get rid of all the x's. Okay. Let's try this problem.
Okay. Okay. So the derivative of tangent secant squared x. Secant. Derivative of secant tangent. Okay. Okay, so we take Okay.
Okay, that seems like that was a good process. So this problem turned out to be similar to the one before. So u equals tangent theta is not a good substitution because what's the derivative of tangent?
Secant squared x.
Now there is a secant squared here, but there's more than just a secant squared. So that would not allow you to get rid of the entire secant to the eighth. On the other hand, what's the derivative of secant theta?
Derivative of secant theta is secant theta tangent theta.
Now, is that in the integral? Well, at first it looks like it isn't. At first it looks like there is no secant tangent, but you used a clever trick. You used a clever trick and you rewrote secant to the eighth as secant times secant to the seventh. And the reason why that's helpful is now there is a secant tangent in the integral. So we have to use that clever trick here. Once we break out one of the secants out of the secant to the eighth, now we do have secant theta tangent theta in the integral. So now u equals secant theta is a good substitution because its derivative does account for the rest of the integral. So that's tricky, but we did that correctly. Obviously, these would be good to go back and try again, but it looks like we did that right. Very good. Okay, good. I'll go back to my screen. Now let's try this problem.
Okay. The derivative of tangent is secant squared x. Okay. Derivative of tangent secant squared x. Okay. Let's see. Derivative of tangent theta. Secant squared theta. Du. Theta. Okay. So what with u? Okay. Let's see. Okay. Oh, let's forget.
Okay, good. All right, well, I was trying to trick you or trap you here because this problem was solved differently than the last one. But fortunately, you weren't on autopilot. You were thinking about the problem separately, and you figured out you needed a different substitution. So that's good. These are actually kind of tricky, but we worked that out. So why is u equals tangent theta a good substitution here? Well, what's the derivative of tangent theta?
Secant squared theta.
And notice how that accounts for the rest of the integral. So in this case, that worked quite well. Okay, so that's actually quite good that you were able to shift gears here and move to a different substitution. That's good that you were not just automatically repeating what you did before. Let's shift back to my screen. So let's compare these two problems. These two problems look very similar, don't they? But they required totally different substitutions. So how can we see the difference between them? So for this substitution, we used u equals secant theta. Because what's the derivative of secant theta?
Secant theta, tangent theta.
And that does appear in the integral.
Right.
Because there's a tangent, and it does appear, if you remember, that secant to the 8th could be rewritten as secant to the 7th times secant. So if you rewrite this as secant to the 7th times secant, then the derivative of this substitution is there, and then that allows you to get rid of all the thetas and replace them with u's. But that substitution would not have worked down here. That substitution would not work here, because what's the derivative of secant theta?
Secant theta, tangent theta.
But that would only get rid of one of the tangent thetas. It
Right.
wouldn't get rid of the other 3 powers of tangent theta. So this substitution would have been a big flop on this problem. So fortunately, you shifted gears and you used this substitution. Because what's the derivative of tangent theta?
Secant square theta.
And notice how that totally accounts for the rest of the integrals. That worked very well. Okay, so how do you know what substitution to make? Well, you could just use trial and error. You could just use trial and error and see what works. You might notice the pattern here, though. What's the pattern between these two cases? You can really only use this substitution when there's a secant squared theta term. You can only use this substitution when there's just a secant squared theta all by itself. So it with no other secant thetas. So you can't split this up into secant squared times secant to the 6th. That won't do you any good because then you haven't gotten rid of the secant to the 6th. So this substitution only works when there's just a secant squared theta term and no other secants. And when does this work? This works when there's a secant theta tangent theta. Here we could rewrite this with the secant theta tangent theta, and there's a whole bunch of other secants, but those are okay. Well, it's kind of hard for me to put it into words, but
Right.
if you stare at these two examples, I think you can see the difference between these. Obviously, if you forget the difference, you can figure it out from scratch, but you might want to just try to figure out what the pattern here is and just memorize it for the test. So you can either figure this out or just try to memorize what the difference is between these two examples. Kind of boiling it down, as far as the test is concerned, if there's a tangent theta term, you're probably going to use this substitution. And if there's a secant squared theta term, you're probably going to use this substitution. There's certainly also many possibilities that we don't know how to solve yet. So for example, if you were given this, I don't think we know how to solve this yet. And I guess we'll never know how to solve this. So sad to say, we're never going to learn how to solve this because this is where the class ends. So I'm sure we'll feel bad about that.
Count 2?
Yes. So at the beginning of the second semester, you go over even more forms of integration. The beginning of the second semester is even more methods of integration. So although there's also some things, I don't even know if this could be solved. I don't have all those memorized. But if it's possible to do this, you would go over this in the second semester. But I think the methods we've gone over wouldn't handle this. Our methods can only handle it if there's a tangent to the first power or a secant to the second power. Our methods only handle tangent to the first or secant to the second so far. Okay, so anyway, those are 2 more things that we might see on the test. I think we made progress on that, but obviously this is something important to keep practicing because it's certainly easy to get confused about the difference. So the way to study this is to compare these 2 examples. These 2 should be learned together.
So it seems like the one with the higher power is the one that you generally use U substitution for. But
and this, I don't know if that's generally a reliable pattern, but as a memory aid, that'll probably work here. As a memory aid, well, let's see. Actually, that's not true because what substitution would you use here?
Okay, yeah, you would use tangent.
So that memory aid won't work. That memory aid won't work. That just was a coincidence for the examples I was giving you. But if you saw this example, you'd have to do the substitution for the lower power. So that was a good try, but that one, it's a little more complicated than that. Okay. So anyway, I think we made some progress with that in the time being, so you can practice that some more on your own. Again, the key thing is to stare at these 2 examples and try to see the difference between them. All right. All right, here's another one. So again, this is we're going to use similar methods here as before, although again, this is maybe a little harder than the ones before. You can start by trying to give it a shot on your screen.
we're taking the integral of tangent of x with respect to x. So what's the antiderivative of tangent of x? What gives us tangent of x? Derivative of tangent of x, secant squared of x. Okay, so oh, that's right. I think we can re-express this as we'll check. Tangent theta equals sine of theta. Okay, cool. So now we can write this as we know the antiderivative of 1 over cosine of x. Well, this is derivative of cosine is sine, no, negative sine. What's the antiderivative of 1 minus 1? Secant of x. Okay. Okay.
Well, that was really good work. That's very good work. So we haven't done something quite like this before. You put the pieces together and really figured it out. So that's good. That's good that you were able to take your time and just figure out something new. So good. Okay. So that wasn't easy, but you did work it out. So let's see here. Let's review the steps. So the key here, let's review this bit by bit.
Mm-hmm.
Do we know a simple rule for taking the derivative of tangent?
Yep.
What's the derivative of tangent?
Secant squared x.
Good. Had we previously learned a simple rule for the antiderivative of tangent?
No.
No, we never knew the antiderivative of the tangent before. Although if you look at it, now we do. What is the antiderivative of the tangent? What is the antiderivative of the tangent of x?
The negative natural log, the negative natural log of absolute value of cosine of x plus c.
That's right, but we never knew that before. So it's important to realize we didn't have any simple rules for this. So then you had a good idea that we'd prepped for. We talked last time about how tangent can be rewritten as sine over cosine. Since we don't know how to find the antiderivative of tangent, we had to rewrite it as sine over cosine. So it's good that you remember that substitution we talked about yesterday. Then you split that up into two separate terms, 1 over cosine x times sine of x. That was also a very important step, so that was great. Then you had to come up with a substitution, and you decided to do u equals cosine x. How do we know that's a good substitution? Well, what's the derivative of cosine x?
It's negative sine of x.
And did that appear in the integral? Yes. That's why it's a good substitution, because that appears in the integral. At least it appears up to a constant multiple. The integral has positive sine x, and the derivative was negative sine x. But those are the same up to a constant multiple, which is good enough. So that was a good substitution. What about thinking about the other substitution, u equals sine of x? That's something we might have considered if this hadn't worked. We might have considered, why don't you write that off to the right, u equals sine of x. You can write that off to the right, u equals sine of x. We could have considered that if the first substitution didn't work. What's the derivative of the sine of x?
That's cosine of x.
So careful, does that appear in the integral?
It does.
It's kind of a trick question. It doesn't. There is no cosine x in the integral. There's 1 divided by cosine x.
Okay.
And it turns out that's not good enough. So that substitution would not have worked. That substitution would not have worked because after all, solve that for du. Solve that substitution for du. That would let you get rid of cosine x dx. But is there any cosine x dx? No. There's 1 over cosine x dx. See, there's a huge difference between cosine x and 1 over cosine x. So you can see that substitution would not have worked because it looks like there's a cosine x there in the integral, but there really isn't. There's a 1 over cosine x. If you tried that, you really wouldn't be able to get rid of the x's. Well, maybe I'm just confusing you by telling you about something that wouldn't work, but I think that would have been a natural thing to try. So, so we can see that substitution, it's not obvious, but when you try it, that substitution doesn't work. Your instincts were correct. That substitution doesn't work because there is no cosine x in the integral. There's 1 over cosine x, and that turns out not to be good enough. On the other hand, your substitution did work because there really was a sine x in the integral. Okay, so your way was correct, and that's a way that you would have to reject if you tried it. Okay, you handled the negative sign here well. That was good. One thing though I would have done here is we should have tried to solve. You have du equals negative sine x dx. Solve that equation for sine x dx. You haven't quite solved that equation for sine x dx. What do you get if you solve that little equation for sine x dx?
Oh, okay.
There's just one more little step to solve it for sine x dx.
Negative.
So I think that would be the best place to stop. That's actually what you did, because you did plug in negative du. You did plug in negative du, so you must have done that last step in your head, but it's better to write it down. We need to solve for exactly what we're trying to get rid of. And then you handle the negative sign correctly. You remember the absolute values. You remembered what the integral of 1 over u was. That was excellent. Okay, so all in all, that was a very good process. I think that was a hard question. That's good that you were able to work that out. Now you can see why we were talking about how to rewrite tangent earlier. We have to know how to rewrite tangent for this type of problem. So unfortunately, the bad news is there's lots of different variations on these trig problems. It's easy to start getting them confused. That's where it's going to be important to practice these as homework.
Okay.
So do you remember what's the antiderivative? What's the antiderivative of sine? What's the antiderivative? What's the antiderivative of cosine x?
Antiderivative of cosine x is sine of x plus c.
Yeah, that's not too surprising because the antiderivative of a trig function turns out to be another trig function. And what's the antiderivative of sine x?
Antiderivative of sine x is negative cosine of x plus c.
That's not too surprising because the antiderivative of the trig function turns out to involve another trig function. Not too surprising. What's the antiderivative of tangent x? What's the antiderivative of tangent x?
It's the negative natural log of the absolute value of cosine of x plus c.
So anyway, I just wanted to point out this is one of the kind of amazing fact that sometimes comes up in math. Where the heck is natural log coming from? So it's just interesting to point out. It's kind of amazing here that we started with a trig function, and all of a sudden we have this natural log function that didn't seem to have anything to do with it. So we're not going to explain why that is, but it's just kind of a cool fact about math that sometimes a function will pop up where you least expect it, and that's what's happening here. I'm sure we didn't predict ahead of time that our answer would involve a natural log because we were doing trig, not logarithms, but it turned out that that's where our logic led us. Okay, so now we know how to take the antiderivative of that tangent function. There was one other thing I wanted to say. Point to the line that says 1 over cosine x times sine x.
Right here?
Yeah. There was a thought process you were going through there that wasn't really the best process. The first thing you did is you asked yourself, do I know how to take the antiderivative of sine x? And you asked yourself, do I know how to take the antiderivative of 1 over cosine x? Those were actually not good questions, because even if you did know how to take their antiderivatives, that wouldn't help you on this problem, because you're not trying to take the antiderivative of sine x, and you're not trying to take the antiderivative of 1 over cosine x. You're trying to take the antiderivative of 1 over cosine x times sine x. Is there a product rule for antiderivatives? Do antiderivatives have a product rule?
No.
But I think you were kind of thinking in your head that you were kind of going to apply some kind of product rule there. So that was a wrong way of thinking that we want to avoid. When you have a product, it doesn't do you any good to try to take the antiderivatives of the two terms separately. When you have a product, it doesn't do you any good to know whether you can take the antiderivative of the two terms separately, because you're not allowed to do that with antiderivatives. If you had a sum, you could take the antiderivative separately. If you had 1 over cosine x plus sine x, then it would be a good idea to try to take the antiderivative separately if possible. But with a product, it's useless to take the antiderivative separately. So instead, your second thought was good. Your second thought was better. You had to use substitution instead. Okay, so let's go back to my screen.
Just one quick question. So if I had used u equals tangent of x, and then I would have, so the derivative of tangent of x is secant squared x.
But is there a secant squared x in the expression?
No, there's not.
So that's probably not the best substitution.
Okay,
Although maybe,
so if I had,
I'm sorry, you were saying? Go ahead.
yeah. So here, maybe I can just a little exercise because I was thinking about it. Tangent of x dx. This question mark. U equals tangent of x. So now we can say definite integral of u with respect to x. And then secant squared x dx. Well, I guess so I guess that doesn't, we can't plug this back into dx because that's not what dx is, but could I isolate dx?
You could try that.
Wait, I think I needed that word. Yeah.
All right, that's legal so far. So let me point out what you have in the line above is u dx. Well, u dx is not acceptable because you have a u and an x. All right, so now you're going to write a new line.
So now I have 1 over. Oh, okay, this is why it's not acceptable.
Now this still is not acceptable because now we still have a u and an x.
Right.
And there's really
So
no good way to get rid of that secant squared x term here.
I would have to use, could I rewrite it as 1 over, no.
Now,
Okay,
actually,
yeah,
do you see, you could rewrite it as cosine squared x. We
right.
reviewed that earlier. That is cosine squared x. But what good does that do you? You still have an x there. So
Is there any
so this
way?
does not simplify nicely because it doesn't get rid of all the x's.
Okay.
Okay, so that's a good thing to try. Oftentimes you can't tell whether a substitution will work without trying it. So that was an excellent thing to try. You can kind of see from the start this probably won't work because what's the derivative of tangent x?
Secant squared x.
But there was no secant squared x in the expression.
Right.
In your class, all the substitutions, the only substitutions that you're going to be using in your class are substitutions whose derivatives are also in the integral. The only substitutions that your instructor is testing is substitutions whose derivative is also in the integral. Now, there are other substitutions in the textbook. There's other forms of the substitution technique that don't require the derivative to be in the integral, but your instructor is not covering that. So you shouldn't need to do that for the test problems or the homework problems. For your class, if the derivative of the substitution is not in the integral, that's not how the instructor was expecting you to do the problem. Okay, but it's a good idea to try that. That's good that you gave that a shot. Like sometimes, to be sure, you kind of have to use trial and error on these to see if these are going to work. As usual, it would be good to check the answer you just got with You could check that answer using derivatives. That would be a good homework problem. Let's go back to my screen. So now we have a whole new set problem here. Notice here, when there's tangent and secant, we use these approaches. If there's only tangent by itself, we used a whole different approach, right? We might compare these now. What was the substitution we used here? Well, if you remember, we used a whole new substitution. So when you have one tangent times a bunch of secants, you substitute in u equals secant. When you have tangent and secant squared, you substitute in tangent. But when you have just one tangent all by itself, you substitute in sine. So it really could get pretty confusing. You can try to memorize these patterns, or you can just try to figure them out by trial and error each time. All right.
Would it be sine or was it cosine?
Did I get confused? I think it really was. Oh, nope. I just made the mistake I was telling you not to make. So we showed that sine doesn't work. You're right. We showed that the sine substitution doesn't work. You have to use cosine instead. Thanks, that's right. Okay. You're correct.
I'm just a calculus whiz. Okay.
I guess so. All right, so let's try this problem.
Okay. Okay, this one is opposite. This derivative is negative sine. made the wrong choice. So if u was sine of x, derivative of sine of x is cosine of x. Cosine of x. That would be cosine of x dx. Derivative of sine of x. Cosine of x. Cosine of x dx. Antiderivative. Natural. Okay, so cotangent x dx, we wrote it as cosine of x over sine of x. Cosine of x times 1 over sine of x. We made u equals sine of x. Derivative of sine of x is cosine of x. du equals cosine of x times dx. We rewrote that. So it was 1 over u times this. So subbed in u, antiderivative of 1 over u. It's natural log, absolute value of u plus c. Subbed in u, natural log of sine of x. Okay, cool.
Okay. Okay. All right. That was a very good process. That was good. That was good work. One thing that was especially good there is that you saw that your first substitution wasn't going to work. That doesn't mean you messed up. You know, sometimes the first substitution just doesn't work. The good thing is that you didn't despair, you didn't give up, you just tried a different substitution. So that's important. Sometimes you have to kind of do these by trial and error. If the first substitution doesn't work, you can't force it to work. You just have to try something else. So that's good that you shifted gears there. By the way, notice you wrote down a little bit more than you needed at the end. Notice that your answer just rewrote your last line. You could have just replaced the ditto marks with integral of cotangent x dx. You don't have to rewrite the answer, but that's okay. That's just a little detail. So let's review that. You used u equals sine of x as your substitution. U equals sine of x. Now what's the derivative of sine x?
Cosine of x.
Is there a cosine x in the integral?
There is.
That's why that's a good substitution. That's a good substitution because of that. Maybe up in the top corner, write down the other substitution you tried. You also tried u equals cosine x.
Okay.
Let me just put that off in the corner as something else you tried. U equals cosine x. Now, what's the derivative of cosine x?
That's negative sine of x.
Now, here's a tricky question. Is there a sine of x in the integral? We don't care about the negative sign because that's just a constant multiple. But here's a tricky question. Is there a sine x in the integral?
No.
Yeah, no. Now, most people would say yes. They'd say, well, it's right there in the denominator. But that's not the right way to think about it. there is no sine x in the integral. There's a 1 over sine x in the integral. And as we were talking about earlier, that's not good enough. There is no sine x in the integral. There's only a 1 over sine x. And as you saw when you tried it, that didn't work. You actually tried it, and that's not close enough. You need a sine x in the numerator, not a sine x in the denominator. Okay, so you can erase that other approach, or you can write down that didn't work. So that's how you could have seen faster, though, that it didn't work. You didn't actually have to try it out so far. You could have just said the derivative of cosine x is sine x, and there is no sine x in the integral, only a 1 over sine x, which isn't good enough. But in any case, you shifted to something else, and that did work. Okay, so now we know how to take that antiderivative. Notice you have to have memorized what's a way to rewrite cotangent.
As cosine of x over sine of x.
And what's a way to rewrite tangent?
Sine of x over cosine of x.
That's right, good. I noticed that on the earlier problem, I think you had to look that up again to jog your memory. So remember, for the test, we have to have those memorized. For the test, we have to have those re-expressions memorized because you can see they're important for these problems. Okay, but overall, that was a very good approach. Like I said, it was very good that you didn't just give up when the first substitution didn't work, and you didn't try to force it to work. You shifted to a different substitution. That's the key to these problems. You have to have a little flexibility for these. Okay, so let's go back to my screen.
Okay.
So one thing you should especially be reviewing today, I think we've made good progress on most. I think you pretty much made good progress and probably have down most of these types of problems. The ones that are tricky now are the ones with trig functions, because there's so many variations, it would be easy to start confusing them. So a good thing to review today is review all the different types of variations that we did with trig functions, especially all these variations of secant and tangent. These three especially, I think, would be easy to get confused. So these three especially, here we used one substitution, here we used a different one. These three especially would be important to review so that we're not getting them confused with each other. We also went over the inverse trig. Remember that it was important not to confuse regular trig. So there's many things that we have to not get confused here. It's important not to confuse trig functions with inverse trig functions. Remember that trig functions are totally different from inverse trig functions. And also it's important not to confuse derivatives and antiderivatives. It's easy to get those confused as well. So that takes some practice to be clear about. Okay, so we made some more good progress today. There's still a few more variations in this section, but I think we went over some tough stuff today and made some good progress on it.